Hello again. This little video is on splitting fields of arbitrary polynomials, not necessarily with rational coefficients. Namely, arguing that they exist. So let's start with a polynomial with coefficients in some field. And we can simplify our life by assuming that it is irreducible. If it is not, well, we can deal with each of its irreducible factors separately. We can also simplify our life by assuming that it is monic. And again, it doesn't change much if it is not. We can make it monic by scaling it with its leading coefficient down. And let's fix d to be the degree of this polynomial. So a field extension of this field of scale is k. This field f is a splitting field for this polynomial. If the polynomial completely factorizes in this field, over this field. So if it can be written as a product of linear terms, some number of them, exactly d, and since we are dealing with a monic polynomial, there is no prefactor, and yeah, so these coefficients will have to be elements of our larger field. So this is a factorization using larger scalars. So informally, you could say that f has, polynomial f has all its roots in this field extension f. And there is a slight ambiguity in what people really mean by a splitting field. So we could make it more concrete by thinking of smallest possible extension. Not just an arbitrary extension where we have enough coefficients to factorize completely, but a smaller such. So that would be coming without saying. And in this episode, I'll just argue that we can always construct such an extension. The construction will be sort of an iteration and a beefed up version of mathematical induction. Let's the starting point is the field of scalars, and the induction step will be constructing a root one by one, constructing each root, constructing a field extension which would harbor a root one by one. So the first step, this induction step, will be just constructing some extension of k where we will have at least one root. So we'll call it k twiddle, and this construction is very easy. We're just assuming that we have an irreducible polynomial, we just take the quotient. That is a field, obviously containing our scalars, and it contains also the special element, the class of the variable t in the polynomial ring, in the polynomial algebra. And it is just an observation that this element is the root of the polynomial in this logic field. Well, simply because, let's look what happens. We declare f of t to be 0, so the equivalence, the congruence class in this quotient ring is 0. But we can also write it as a polynomial evaluated on the class of t. And that is a statement that this class is a root. So here's the justification. Now by Bezout lemma we can take the polynomial f, and so now the kind of second step of the induction second part of the induction step is to use the Bezout lemma to factor the polynomial, it will look funny, into a product of the linear term corresponding to this root, and something else. So the something else will have to be using coefficients from our extended field. And the induction step, the sort of the continuation of induction, is to look at this and look at its irreducible factors, whatever it has, and then continue the process with them. And since we are decreasing the degree, the process cannot go forever, it has to stop at most after d steps. We will have all the roots in the iterated extension, and that would be the splitting field. So that is it, that is the argument. One immediate consequence of it, one nice feature we could see, say for this splitting field construction, is that the degree, this d, the degree of the polynomial, will divide the degree of this extension. Well, it is simply because the first step produced the extension of the scalars k of degree d. This quotient field has degree d, has degree equal to the degree of the polynomial, and since it sits inside this is exactly k twiddle, and it sits inside our splitting field f, the degree over k of this splitting field f has to be divisible by the degree of this extension, which is d. So that is it. See you later.